transfer. And in that one-dimensional steady state conduction. In this, we'll look one generalized problem. This dotted one is a thermodynamic system. In other words, a control volume or an infinitesimally small element of distance dx. And the coordinate systems are at the axis of symmetry of the fin. So this total distance should be 2y. Above x, it should be a y. Below x, it should be negative y. So total distance is 2y. This is the depth. And this one is the length. And this is a shape of the fin, which is given function. Okay, the shape of the fin is given as a function, and this fin having a temperature at the wall, which is TW. This is the wall. Here it will be a wall. So the temperature of this wall. So at y is equals to 0, temperature of wall is given, and this whole fin is subjected to the atmospheric temperature, which is at T infinity. Now, in such case, from the first law of thermodynamics, we know that del Q of a thermodynamic system should be equals to dE plus delta W. In this case, E is defined as the internal energy plus kinetic energy plus potential energy. And this kinetic energy and potential energy is 0. So you get essentially del Q du plus del W. Also, in this system, the work done is also 0 because uh, it is a steady state system. Also, the change in the energy because of the steady state nature, this is also 0 because of steady state, and this is 0 because there is no work in the above system. So in total, del Q must be equals to 0. So whatever Q balance has to be there. So if you take this element and take a Q balance, I mean heat balance, then you can get a governing equation, and which also can be derived from the equations we have derived earlier. Okay, these two are not different things, they are same. So let this is some theta, and so there will be a Q in, and this is a delta dx. So at this space, Qx plus dx. Now, since the thickness, the variation along the y direction is very small because of the thickness of the fin. There is no scope for heat to transfer because of conduction, because of, I mean, scope in the sense it is negligible. Okay, because of the small distance in y direction. And in this case, we are considering depth is equals to 1 unit depth. Okay. So since the y direction there is no heat transfer, only x direction there is heat transfer, this problem is a 1D problem. But we can consider this is a conduction mode, but there can be convection happening, and which which is not a directional because there is no gradient involved in it. So we can say that there may be a Q convection and there may be Q convection from other surfaces. Also maybe a convection at this surface also is possible. This surface is already a wall surface, so other surface other than this there may not be. So balance del Q is equals to 0 is nothing but equals to Q in minus Q out, in minus out equals to 0. So you can write Q in is equals to Q out, and that can be written as Qx plus, and suppose there is a generation, Q generation is also there. That case also we are going to consider, for example, then Q generation, and Q generation is a volumetric phenomena. So area into dx, cross-sectional area into dx is the volume. This is a in quantity. Generation is also a input to the system, and output of this system, whatever is going from the system. So Qx plus dx is the heat going out of the system, and twice Qc is a heat going out of the system due to convection. Here Qx plus dx can be obtained by taking first two terms of Taylor series, and we can write Qx plus dx is equals to Qx plus dx del Qx del x. Plus this we are neglecting, so we'll write only two terms of the Taylor series. Truncated Taylor series. This is a truncated terms. And QC uh, can be obtained. QC can be obtained from Newton's law of cooling. Newton's law of cooling. Okay. And which is equals to QC is equals to Hx As T minus T reference. And here we can see that Hx is a heat transfer coefficient as a function of x along this wall. Along this wall. Okay. Along this wall, the variation of Hx. Along this wall, variation of Hx. This Hx. And the surface area is the surface area of the convective heat transfer. So this surface area, this you can write as dx divided by cos of theta into 1. Okay. So dx cos of theta will give you this yellow surface, and 1 is the unit depth in the other direction. So you have this is a unit, so you can get the surface area. And T reference is a T infinity, which we are having here. So T infinity is taken as a reference. Okay. Okay. And Qx can be obtained from Newton's Fourier's law. Sorry. Fourier's law of heat conduction. Fourier's law of heat conduction says Qx is equals to minus K dt dx, isn't it? So substituting this, upon substitution, this is A, where A is a cross-sectional area, and which is nothing but equals to twice of yx into 1. So you substitute this, and upon substitution, we get d dx. We can write it as is ordinary derivatives 2yx dt dx dx plus twice hx dx. X is a suffix, okay? Cos phi t minus t infinity is equals to q generation twice yx into 1. So considering if K, K is a thermal conductivity activity of solid film is constant, then we can take this constant out of this derivative, and we can write these expressions as k 2y x d2t dx2 plus 2k dyx dx plus 2yx q gen minus 2hx dt minus infinity divided by cos phi dx is equals to 0.
Excuse me, sir.
Yeah,
Sir, in the second term, 2k dy by dx, it shouldn't be multiplied by dt by dx again, because dot product dt by dx is there in the first term.
where
The last line, second term.
this one?
Sir, no, sir, the second term, 2k dy by dx.
2k,
In, d,
yeah, one
in,
term should be there, dt
into
by dt,
d into dt.
dt by dx. So this is for constant k case, okay? So this can be, generalized 1D steady state equation for this spin problem specifically, and y can be anything, okay? So it can be a trapezoidal type of fin, The fin can be of this shape. The fin can be a parabolic fin. Okay. The fin can also be triangular fin. Fin can also be a rectangular fin. So depending on the different shapes, that is the functional relationship of y, you can get different, expressions for different fins, and you can solve these expressions. If we know these values, these constants should be known. Dyx will also should be known again. So this is known. Dt dx is unknown, and these things also should be known. Hx, dt infinity, t is unknown. So unknowns are this. T is unknown. Wherever t is there, that is unknown. And we know that we can use any discretization scheme for second order term, any discretization scheme for first order term, and it is a discrete value at that particular node. Now, what boundary conditions we can have? So, boundary conditions. Excuse me. So, this equation, if you see this equation A, since equation A is a second order, we can say ODE, we need two boundary conditions. Okay. So, one boundary condition at x is equals to 0, and at x is equals to, if this is the length L, x is equals to L is needed. So, at these two locations, this boundary condition is there. At x is equals to 0, already there is a fixed boundary condition because of the nature of, because this is fixed to a wall, and either there can be a flow here passing through this, which may be at some TW temperature. So that, and assuming that there is no, this thickness is very small, we can assume that TW is equals to T wall. Whatever value of this fluid temperature will be there, it can be also like that. But let us assume that we do not know the situation, but this is at T wall. So this is at T wall. This is fixed. So temperature T is equals to TW. Now, what about this condition? What about this condition here at x is equals to L? At x is equals to L, there can be various possibilities. Okay, if it is not specified. One thing is that it is exposed to a fluid here. It is exposed to a fluid, and at the junction between a solid fin and a fluid, that is maybe air, what do you see is that whatever the heat is being conducted, that is Q conduction is equals to Q convection. That is a one thing. Okay. So one boundary condition can be minus K dt dx is equals to H, whatever H is there present, H T minus T infinity can be a one boundary condition. on x is equals to L. Also, it may be that uh, heat transfer, maybe heat conduction may be specified. So there may be Q conduction may be specified. In that case, no need to consider the balance. So if the value of heat flux is specified, then you can write K dt dx. So this is another boundary condition. One boundary condition is this, another boundary condition. If it is an insulated boundary condition, means Q conduction is 0, then in that case you can write Q dt dx is equals to 0. This is another boundary condition. Fourth boundary condition can be the T can be itself T infinity. Okay, T can also be T infinity. And this is possible only when this Q, when you say Q, this delta T is equals to Q, this resistance, resistance, conduction, convective resistance. But this convective resistance is very high, uh, so this delta T is very small and Q can be very small. And delta T is very small means T infinity, T minus T infinity is they are nearly equal. This T and T infinity should be nearly equal, then only temperature at the surface, T surface, T surface minus T infinity. So T surface can become T infinity. So these four boundary conditions are possible at this location. Okay. This boundary
So,
condition you see here, yes.
so one doubt. The condition last condition you wrote, T equal to T infinite,
Yeah.
isn't that for infinitely long fins? This condition.
Uh, Not exactly. We are saying that it is only in the case when this resistance is, you know, this Q is written as a in terms of convective resistance. This is a convective resistance.
So convective resistance 1 by HA.
1 by
That
HA. 1 by
okay.
HA. Yeah.
Okay. That fine.
So, in that sense, that is a cross section area. Okay.
Hmm. Got it. Fine.
So, yeah. Okay. So, this condition is our, in general, Robbins boundary condition, isn't it? Robbins boundary condition. This is our Neumann boundary condition. And this is also Neumann boundary condition. When this 0 is specified, it is called a homogeneous Neumann boundary condition. And this is a Dirichlet boundary condition. Dirichlet boundary condition. Robbins. Now, based on the situation, you should be in a position to identify what should be my boundary conditions. Okay. That should be a objective when you learn a CFD. There are many CFD people who teach the subject, but they don't know how to formulate a problem, how to give a proper boundary conditions. They only know only for their specific problems. But when new problem comes, they are not able to generate proper physical boundary conditions. Such a situation should not happen. So please give importance to these things. Other possibility is also there. One more possibility can also be, like we said, conduction and convection. So it is also possible as Q conduction, okay, uh, can also be equals to the radiation at the surface. If radiation is a dominant one, then Q radiation may be possible. Another thing is there may be a directly radiation Q, I mean, Combination of radiation plus QC can be also possible. So that is dependent upon the situation at hand. Okay. So as we were talking about Ts is equals to T infinity condition, there was the basis for using it was this. And to use this boundary condition, we need to find out this resistance 1 by HA. Okay, H is average heat transfer coefficient at this surface. So if we found that this Q is very, very small, then in those conditions, we can talk about, okay, we can talk about the T is equal to T infinity. Similarly, if there are radiations, so we have to check whether radiation is significant or not, and then we can apply. So if Q radiation is there, we know that Stephen-Boltzmann law can be used, and yes, Stephen-Boltzmann constant, and F12 is a view factor which is taking into account resistance due to surface emittance and geometrical configuration. And you can have Ts to the power 4 minus T infinity to the power 4. This is also another boundary condition which can be specified here. And this is also Robbins boundary condition. This is also Robbins type of boundary condition. Now, if you see these boundary conditions, red one, they are, if K is constant, H is constant, they are all linear. Okay, they do not have a power of T. But if you see this boundary condition is a highly non-linear, it is having a power of T to the power 4. So these non-linearities present in this Ts to the power 4 makes this problem non-linear. Even if this equation, after considering K, 2y, all these constants, K constant, and only equation d2t dx to dt dx, and these values given and these values given, your problem may become non-linear because your boundary conditions are non-linear. Okay. So non-linearity doesn't mean that only the governing equation is non-linear, but also your boundary condition also should be non-linear. Then only the problem becomes, or any one of them becomes non-linear, the problem is non-linear. Anywhere in the governing equation or boundary condition, non-linearity is there, it means that the problem is non-linear. Okay. So with this introduction, we'll move on to one-dimensional heat conduction. In rectangular domain. So we consider a fin, rectangular fin, as our example. And we consider unit depth similar to the previous one. So this is a unit depth and this is a length L, capital L. This is x is equals to 0 and x is equals to. Okay. So K constant and Yx is nothing but equals to half, and Hx is nothing but equals to H bar average heat transfer coefficient K d2 dx2 minus 2H bar dx cos phi t minus t infinity can be written. And we can again know that this cos phi dx by cos phi 1 is a ax, so we can rearrange that because we do not know this theta or phi. What are theta or phi? So 2H bar as can be written as k and t minus t infinity here. And we know that perimeter is 2. Perimeter is equals to 2. And area is equals to 1 into 1. So uh, we can represent as is equals to P by A. Okay, P by A. And we can write this equation as K d2t dx2. And I take this K also. I divide this whole equation by K and we consider 2. So 2 I have combined with perimeter. So I'll just write it like H bar. P is a perimeter. K is a thermal conductivity. A is a cross-sectional area. T minus T infinity. This is the equation after you consider these assumptions and these assumptions. You get a Finn equation. This you can say a Finn equation. Rectangular Finn equation. Now we would like to solve to this problem. So we need boundary conditions and say boundary conditions are given. So at x is equals to 0, obvious boundary conditions t is equals to whatever the t wall is, and at x is equals to L, we need a boundary condition. And say now in this case, we are considering for our purpose to solve this problem, a one boundary condition, that is here the q x is equals to 0. Okay, so which means that dt by dx is equals to 0. K divide 0 by k, that goes 0. So k cannot be equals to 0. So dt by dx is equals to 0. And for this problem, we know the analytical solution. Okay. Though we know the analytical solution for this problem, our interest is to solve it numerically. Okay. So that we can compare our numerical solution with this analytical solution and see that numerical solutions are also equivalent to getting the solution by analytical method. Now, when the analytical method, in such case, when the analytical methods become fail, then numerical methods can replace analytical method and equally can give a reasonably correct results. So analytical solution for this case given is, you can refer your any standard heat transfer book, T infinity, T wall minus T infinity is equals to cos H m L minus x. L is length of the film. L minus x divided by cos h ml. M is M is defined by this this one. Okay. M square is equals to HP Ka. So M is equals to root H bar P Ka. Okay. Okay. So this is the equation now. Suppose we want to solve. So one procedure we follow is that non-dimensionalization. Okay. This may or may not be necessary. Even we can solve without non-dimensionalization of this problem. I'll just give you a procedure. We'll see non-dimensionalization. So rather than saying step number one, I'll just say non-dimensionalization. So to non-dimensionalize this problem, what parameters you may need? Some non-dimensional temperature, which can be given as T minus T reference divided by T wall minus T reference, isn't it? And which can be written as T minus T infinity is or T reference and T wall minus T infinity. This can be written as a non-dimensional temperature. And the X can be written as some non-dimensional X, capital X can be written as the dimensional X divided by the characteristic length of the problem. So in this case, the characteristic length of this fin is the total length of the fin in which in the direction of which things are happening. Okay, so heat is transferred in this direction. So much of the changes are happening in L. So L is a characteristic dimension, not the Y direction is a Y direction, because in Y direction much changes are not there. So L is considered as a dominant and characteristic dimension. So there is a experience and just some sort of analysis is needed in order to get these values. So once you substitute this, you find that this equation turned out to be d2 theta dx capital dx2 minus m square. M is already defined as h bar p. M square theta is equals to 0. And since governor equation is also non-dimensionalized, then boundary conditions also need to be non-dimensionalized. So x is equals to 0. You have t is equals to, means theta is equals to 0, and t is equals to tw, so that is nothing but equals to 1. Okay, so theta is equals to t minus t infinity and t ball minus t infinity, and at t is equals to tw, which is nothing but equals to tw minus t infinity divided by tw minus t infinity is equals to 1. And at x is equals to L, theta, that is nothing but del t by del x. So del t by del x is del theta by del x, which will be equals to 0. You substitute del t by take the derivative of del t theta, and with respect to capital X, you get 0. Okay, so this is a new problem now. Okay, L is nothing but 1. Here x is equals to 1. Capital X. These are capital X's. Capital X is equals to You understand this, okay? Capital X is equals to uh, L, capital L. So this is essentially 0. X is equals to 0, 0 by 1, L, 0. This is nothing but X is X by L, capital X by L. This is L by L, so 1. Okay, so this problem, non-dimensional problem is like this. Minus m square theta is equals to 0. With theta is equals to 1 at capital X is equals to 0 and d theta by dx is equals to 0 at x is equals to 1. Okay, this is a non-dimensional problem. This is a non-dimensional problem. You apply any method here, any method for discretizing second order ODE or PD, and you can get. Okay. So any ODE method you can use. So any ODE method, any mode ODE method is any ODE method. So you know the ODE methods like Newton's method, Runge-Kutta method. Okay, but we are interested in, but we are interested in applying the finite difference method. Okay, so let us do with this equation without non-dimensionalization. Okay, non-dimensional. Otherwise, you will always think that we need non-dimensionalization. Some books talk about non-dimensionalization initially, so it gives some sort of impression that always you have to do non-dimensionalization. That is not the case. You can use dimensional equations also, and you can discretize them and get the solution. But when you use non-dimensionalization, we know that there are certain advantages associated with non-dimensionalization. So we can utilize those. And how much time do we have?
Uh,
Hello?
Sir, it's 2 o'clock already, sir.
Okay. Okay, so we'll do it tomorrow.
Sir, sir, am I audible, sir?
Yes, yes, Vignesh.
Sir, this can I ask a doubt regarding this lab, sir? Computational lab.
Oh, what happened?
Sir, yesterday fully I tried to get that similar results, sir, for P theoretical and in
You
CFD.
you're not able to get, isn't it?
Yes, sir. Can I share my screen?
You can, but you will have to try that. Okay. If you are not getting means you are doing wrong. So where is the wrong that you have to identify? But you
Sir,
can share. No, you can share, but don't share in order to get the solution from me. Because I can give you the solution, but that will not work, na?
no,
This is okay, fine. Yes.
no, sir, not like that.
Uh,
Sir, because it is
will
even
that
if I
means
put a minimum value or maximum value, it is constantly maintaining distance.
your voice is
Sir,
breaking. Viknesh, your voice is breaking, but
sir, this is
what
for
is what do
P2,
you
sir.
what you said? Max and minimum?
Yes, sir.
P is equals to
Just
2. Okay,
a minute.
capital P. But then have you taken conditions properly?
Just a minute, sir. Just a minute, sir. Hello. Am I
Yes.
audible, sir?
Yes, you're audible.
Yes, sir. All the conditions I have actually given, sir. The
Ah.
mesh conditions, this I
See,
got
that
for
will be already
0.12 meters, sir, mesh.
that you feel that you have given, but there must be some problem.
So I try.
Okay.
Sir, actually, I'm also facing the same thing, sir. I've
Yes, sir.
got the
Because
great
it is not
convergence.
at all
Ah.
I've
inside
You got the grid convergence, but
Sir, got the great convergence, sir. But the thing is, the for the this thing, the analytical value for with the formula, sir, the
ah,
maximum value is coming somewhere around 1.3, 1 point something like that. But
sure.
for this
Ah,
ANSYS simulation,
ah.
the thing is always coming around 1.1.
here.
And I'm
Okay,
doing this
no
for
problem.
P.
See, no problem because
So,
it's a numerical solution, isn't it?
yes, sir.
So do
1 point.
not, do not try to get exact match.
So that's the thing, sir. It's not it's not coming an exact match. My graph is also
No
coming
problem, no
similar like
problem,
this.
no problem. That is the effluence error, isn't it?
So,
So you have
like,
to
there
increase
can be error.
higher order method. Yes, there can be error. Yes,
Uh,
possible.
First order and second order, both of them, like there's a little difference, sir, but none of them are matching to the formula solution.
Possible. That is possible.
And my graph, the red color graph is the ANSYS one, and the blue color graph over here is the one with the formula.
Hmm.
My
Yes, sir.
graphs are
Because
coming
more
very
or less
similar
they
to
are
this.
similar, sir.
Yeah, there will be some
The
error, but we have to then quantify the error.
So the trend is the exact same.
Uh,
They are
No,
following, both of them are following the
the
exact same trend, sir, but
uh,
both of them are not matching.
uh.
That's the problem, sir. So our doubt is that is it going to exactly match? Like, is it going to exactly overlap in
sir,
this
but
cases?
Hello?
otherwise, if you see the
Yes, sir.
sir here boundary is also forming, sir, in contour. If,
What happened? It has
yes,
come
sir.
or
Sir,
not?
in contour also yesterday I showed you, no, sir, this one.
Oh,
Yes,
it
sir.
hasn't come. Okay, okay. Okay, okay, okay. I'll check again. नहीं मैंने yeah. Mm-hmm. I
Yes, sir.
Sir,
Because
your voice is breaking, sir.
the PL are coming properly, sir. Only problem is it is not merging.
yeah, Viknesh.
Yes, sir.
Ah, so that
Sir, now
those
your voice is audible.
trends are
Yes.
fine. Yeah, trends are fine, right?
Yes,
So
sir.
Yes,
It
sir. The
is.
trends are fine.
did not cry CRY for getting the exact match. Okay,
Okay, sir.
first you
Okay, sir.
compare.
Fine. Fine.
Okay, there may be either maybe a fluence problem or maybe somewhere you might not have given proper values of the some values, viscosity or somewhere you must have missed some values. Okay, so that may also be
Yes, sir.
reason. But if you are getting trends, you should show those trends and grid independence. These things are important. Okay. Procedure is important.
Okay.
Reaching to the target, then we'll see once you reach the target, then you have to start thinking what is wrong, where is wrong. Okay. So don't think that the
Yes, sir.
solutions are wrong.
There was one doubt, sir.
Hmm.
because we first I gave 0.12 mm, sir,
What is
for
0.21 mm?
element size.
Element
Element
size.
size, grid size.
Element size.
Yes, sir. So I was able to get the deviation on the right hand side. That is, there was some little deviation. As I decreased the
Yes,
element
you
size, the
see,
deviation was large.
decreasing the delta x doesn't mean that you will always get convergence. I mean, good results. Why? Because
Okay.
once you decrease the delta x, your round of error starting increasing, isn't it?
Okay.
Truncation error decreases, but round of error increases. So two reverse things are happening. That is why it is called as optimization.
Okay. So I thought if we reduce the mesh size, automatically we'll get accurate results.
No, but there will be at least, no, that is not the case. There will be at
Okay.
least a situation where two grid sizes will not change. We are not we are not trying to get delta x small such a way that your experimental data matches. No,
Okay.
we want a situation
Okay.
where our result should not deviate if we change the grid size. Okay, so
Okay, sir.
suppose I take
Oh.
n, 2n and 4n grid size, and I observe that n and 2n has a difference, but 2n and 4n do not have difference, then I say that 2n is a optimal grid. And then we do not
Okay.
change below that.
Yes, sir.
If
Understood.
not, then we change. If not, then we change. If there is no difference in all these three grids, then again we consider 4n as a n grid, and then 2n, 4n, like that we decrease and see. This process you have to continue till you get converse, I mean optimal grid size. If you obtain that n, 2n, and then 4n, and still lesser grids, they are giving you wrong results. It means that you are in the domain where you are making more round of error. So whatever the n you have considered in the previous, that is essentially maybe a 4n grid. Okay, you
Yes.
understand? So
Yes.
4n divided by then 2, and then divided by 2, you should take medium and coarse grid. You understand? You have to go in that direction, not always in this direction.
Yes.
Okay.
Thank you. Thank you, sir.
Sir,
Yeah.
sir, I completed till 810. 810. I till now I don't get the convergence, sir.
Yeah. So that is
Further
what
I go
I'm
more.
saying. The grid you started with n,
Okay.
maybe, and before n, so n is 60 maybe. So maybe 30 or maybe 15 grid you should try. You understand? What you are doing is 60 and then 120 and then 240. Then again you are increasing. But now you should try going in the reverse direction, back direction. Because you are now since nothing is changing, error is increasing. It means that with decrease in delta x, your round of error is increasing.
Okay.
Okay, so you should take n by 2 and n by 4. Okay.
Okay.
So n by 4 will be coarse grid, n by 2 will be medium, and n will be fine. Then you will see that n by 2 and n means this present grid will not have much more difference. Or still if it has, then you go again in that direction, reverse direction. In the manual, I have told you only in one direction. But in general,
Okay.
most of the time, people don't give much higher grade. But this problem is very simple. RE is very small. So maybe you might have given very large grid size. Okay, because to make that boundary layer and this thing. But since there is no much boundary layer effect here.
Sir, actually, I gave 1 meter for a grid size for
Ah,
P is 0.
yeah, but
Then
your
I got
grid,
the result exactly merging.
yeah, your grid size may also be very high. And that also
1 meter
when you give 1 meter by 1 meter, then your values may be correct. That is also possible. When you have give 1 meter by 1 meter, then that delta px calculation, dp by dx calculation, that calculation must be correct. But when you are changing dimensions, you might not have calculated dp by dx correctly. That is also possible. So you have to cross check yourself. Okay,
Yes.
here is a
Okay,
wrong.
sir.
Okay. And then after finding out, only we should proceed to certain options. Like now we are talking about this option. Rather than going from n to n, 4 and 2, we should go in the other direction. Okay.
Thank you, sir.
Yes.